Hi everyone. In this video, I'm going to be going over two problems related to momentum conservation in collisions. And we're going to be using the formula P before equals P after. Question 1 says, two brand new ice skaters have a collision on the ice. Esme, a 21 kilogram skater, overestimated her new abilities and was gliding across the ice at an ambitious 4.6 meters per second. Octavia, a 37 kilogram skater, who was blissfully unaware of Esme's presence, was gliding in the same direction at a more modest speed of 1.2 meters per second. When Esme collided with the unsuspecting Octavia, she clung to her for dear life. At what speed did the pair end up traveling at together after the collision? I started, of course, by circling my numbers and units, and I underlined the unknown. They're asking me at what speed did the pair end up traveling at together after the collision, so I know I'm solving for v. There's a few words that I thought were important. I saw same direction, and I didn't see any other direction words like left or right, so I'm just going to keep all my numbers positive, and that's going to make my life a little bit easier. I also saw together after the collision, which means that this is a special type of collision where the two objects, in this case these two people, stick together. And then because they said after the collision, I'm probably solving for some sort of final velocity. This problem gets a little complicated because there's two different masses and two different velocities that are given to us, and then we're even solving for a third type of velocity. So to make sure I know kind of what I'm looking at, I labeled the masses as M1 and M2. So I wrote M1 equals 21 kilograms, so Esme is going to be object 1, and Octavia is going to be object 2, so M2 equals 37 kilograms. I did the same thing for their velocities. V1, which is Esme's velocity, was 4.6 meters per second. V2, which was Octavia's velocity, was 1.2 meters per second. So the 1 and the 2 here are called subscripts, and I just write them small next to the main variable that I'm using. It does not mean that I'm going to be squaring. When it says m2, that's not the same thing as m squared. So it's just like a certain type of mass, or the mass for the certain object. Now, I know that I'm solving for v final because it says they travel together after the collision. And I don't really have to specify 1 or 2 because they're both going at the same speed because they're stuck together. So for all my collision problems, I'm using P before equals P after, but I kind of don't really know the momentum before, and I also don't know the momentum after. So I have to kind of expand this equation. On the left side, I'm looking at P before, and that means Esme's initial momentum plus Octavia's initial momentum. So this section represents Esme's initial momentum, m1 v1. And that's just because P equals mv. So the formula P equals mv is on my reference guide, but this section where you expand the P before equals P after is not on your reference guide. So this is usually something you have to figure out on your own. I have two different objects, and so I have two different terms here. And they're traveling separately. They're not stuck together. So I have m1v1 plus m2v2. That's going to be the total amount of momentum before the collision. After the collision, they stick together. So it's really going to be the total mass, m1 plus m2, traveling together at some final velocity. Now I can plug in my numbers. And you can plug the entire left side into your calculator at once if you would like. I'm doing it in a few steps. So I did 21 times 4.6, that gave me 96.6, and so on. And I did it like this so I can check out my initial momentums and put them on my graph. So I got 96.6 kilograms times meters per second for Esme's initial momentum, and I got 44.4 kilograms times meters per second for Octavia's initial momentum. It's just important that Esme's is a higher bar graph because she has more momentum, and it's important that they're both pointing up or in the positive direction, because I decided that I'm using the positive direction. And in the problem, it says they're both traveling in the same direction. All right, so let's pick up where we left off. 96.6 plus 44.4 equals 58 VF. I just added up the two numbers on the left, and I got 141 equals 58 VF. And my last step is dividing by 58 on both sides, and I get my final answer. Velocity final equals 2.43 meters per second. So that's how fast both of them are traveling together at the end of the problem. But they're not going to have the same momentum as each other, right? The total momentum will stay the same because that's the rule. Before and after the collision, total momentum must stay the same. But they don't have the same mass, so even though they are traveling at the same velocity, Esme is going at 2.43 meters per second. Octavia is also going at 2.43 meters per second. But Octavia has more mass, so she has more momentum. I added in the numbers that I got for momentum. That's not really part of the problem. So if you have some extra time, go ahead and calculate this and see if you got the same answers as me. But what's more important is that you just show that Octavia has more momentum compared to Esme here. Now the question asks, how did you modify the formula P before equals P after to match this problem specifically? What I'm talking about here is this section. The M1V1 plus M2V2 equals, and this whole thing. So I just want you to talk about why we used this specific formula. Again, this isn't a formula that's on your reference guide. It's something we have to create each time for each new collision problem. So why is it that there's two separate terms on the left and then just one on the right? Why are you adding the masses here, but you're not adding the masses on the left? So that's what you should be talking about for that question. Then it asks, in your formula, how did you distinguish between the mass of Esme and the mass of Octavia? And I'm talking about this notation. Remember, M1 and M2, that 1 and 2 are called subscripts. Let's take a look at question 2. A 6-kilogram puppy is riding on a skateboard, 1.4 kilograms, moving at a speed of 1.2 meters per second. While gliding along, the puppy sees a squirrel and jumps off the back of the skateboard with a speed of 0.5 meters per second backwards relative to the ground. What is the speed of the skateboard just after the puppy jumps? So I'm going to start by annotating using cubes. I'm circling my numbers and units, underlining my unknown, and boxing the keywords. I put a box around riding on a skateboard because that shows me that the puppy and the skateboard are quote-unquote stuck together. So they're starting attached to each other, which means I want to add the masses in the beginning. I put a box around backwards because that tells me the 0.5 meters per second will be negative. I put a box around skateboard because they said, what is the speed of the skateboard? And that I could have been solving for the speed of the skateboard or the puppy, so it's important to know which one I'm solving for. And then it's important to know after, because that means I'm solving for the final velocity of the skateboard. I'm going to do the same thing with M1 and M2. In this case, I called object 1 the puppy and object 2 the skateboard. I wrote down just one value for V initial. So I didn't write V1 and V2 this time because they're both traveling at 1.2 meters per second. So I just called that VI to show that initially they're both traveling at 1.2 meters per second. Now it gets even more complicated because I have two V finals. So I'm going to write V1F equals negative 0.5 meters per second. And that's because that's my final velocity for object 1, which is the puppy. V2F is my question mark, and that's because I'm solving for the final velocity of object 2, which is the skateboard. So I'm starting with my same formula, P before equals P after. But this time it's kind of reversed. The two objects start off together and they end up separately. So when they start off together, that's the thing where I add the masses and multiply by velocity. And then when they end separately, I'm doing two different terms, m1 v1 final plus m2 v2 final. So this term represents the momentum of the whole system before, and then this is just the momentum of the puppy, and then the momentum of the skateboard. When I plug in my numbers, it looks like this. I just plugged this into my calculator. Make sure you're doing 6 plus 1.4 in parentheses, or just adding it in your head before you multiply by 1.2. And then 6 times negative 0.5 became negative 3, and my next step is going to be adding 3 to both sides to get rid of this. So now I have 11.88 equals 1.4 times V2 final, and my last step is going to be dividing both sides by 1.4. So my answer is 8.5 meters per second. That's how fast the skateboard is going just after the puppy jumps. And so the skateboard is going forwards, even though the puppy was going backwards. So, and I know that just because it's a positive number here. All right, so these are my graphs. Again, you don't necessarily have to go back and calculate exactly how much momentum each object has, but you should be able to realize that the puppy has more momentum than the skateboard. Initially they're traveling at the exact same speed, but the puppy is more massive, so it should have more momentum. Afterwards, the puppy is going backwards, so it's important that you draw your bar graph in the negative section of the graph. And the skateboard gained a lot of momentum because it's going forward much faster now, 8.5 meters per second. So that's a pretty significant increase in momentum. So this is what your graphs should look something like this. So then it says, why did you have to modify the formula P before equals P after in a different way for this problem? I'm just referring to these two equations you wrote. So this one has two terms in the beginning for question 1, m1v1 plus m2v2. But then it just has one term at the end where you added the masses and multiplied by the velocity. And then here it was kind of the opposite. So try to explain why, what about the problem made you kind of write the equations that way. And then for the exit ticket, I'm giving you this third hypothetical problem. What if we gave you a problem with two objects that started separately and then collided, bouncing off of each other? How would you modify the formula P before equals P after to match this type of problem? So it's going to be the same idea as something like this, but neither one of these would work. So you have to modify it again to try to make it match this idea that the two objects start separately and they hit and then end separately because they bounce off of each other.